Hello everyone, my name is Anil Seni and I would be presenting our lecture on ethical considerations in AI. This lecture is part of a course at Sinai Medical Center titled Artificial Intelligence HAI 100B. And here is the roadmap for today's lecture. We will discuss four major questions that represent fundamental ethical challenges related to using AI in fields such as healthcare. We will first discuss fairness and bias, which is related to whether a given model discriminates against a subpopulation. Then we will focus on the issues concerning privacy protections while training and using a given AI model. And after discussing the concept of AI alignment, we will end our lecture by considering some other possible social impacts of using AI. Let us now begin with fairness and bias, which is one of the most studied ethical issues in AI. Algorithmic fairness means that a model should perform equally well across different subpopulations. And a model is said to be biased or unfair when it outputs less favorable predictions for certain communities without any valid reason. In this context, certain features within a dataset, such as age, gender, and religion, can be termed as sensitive features. And the expectation is that the models would not use these features to create discriminatory outcomes. In other words, models should not use only these features to make predictions. Essentially, models produce biased predictions when they learn to associate sensitive features with the target variable. This is one of the most famous examples in AI fairness. Compass is a tool used in the US criminal justice system to predict recidivism. It outputs scores that are used to inform decisions about who can be set free at every stage of the criminal justice system. Researchers analyzed risk scores assigned by this software to more than 7,000 people in Florida. What researchers found after the analysis was that Black defendants were 45% more likely to be labeled high risk than white defendants, even when controlling for prior crimes and other factors. Essentially, although the model appeared objective, it encoded systemic bias. Now, where does this bias come from? It can come from multiple sources, four of which are listed here. A given model can produce biased predictions when the data itself is biased, or in other words, it encodes historical discrimination against certain communities. Another reason might be that the data is imbalanced, which means there is an underrepresentation of certain groups. Modeling choices can also produce biased predictions by choosing decision thresholds that favor only one group. More on this later. And last but not least, a limited feature set also plays some role in the sense that when not given enough features, the model can learn false relationships between the sensitive features and the target variable. For example, if a healthcare model lacks socioeconomic data, it might incorrectly attribute health outcomes to biological differences. Let us use this illustration to understand how modeling decisions can induce bias. This figure displays two decision boundaries. Assume that circles and triangles represent two applicant groups for a job, and each point's true label, whether accepted or rejected, is indicated by its solid fill color, where solid red color means its true label is rejected, and solid blue color means its true label is accepted. For both boundaries, the areas above the diagonal, shaded in red, denotes a rejection prediction, and the area below, which is shaded in blue, denotes an acceptance prediction. While both decision boundaries yield the same overall accuracy, their predictive performance varies between the two groups. The accuracy is higher for triangles and circles for the leftmost boundary, whereas the accuracy is the same for both groups with the rightmost boundary. This example illustrates how modeling decisions, such as selecting decision boundaries, can negatively bias predictions against certain groups. It also shows how modeling decisions can reduce disparities without sacrificing overall predictive performance. Now, a common idea to make models more fair is to just remove the sensitive attributes. But this does not work in practice. Why? Because of the presence of redundant or proxy features. These features are correlated with sensitive features and can induce bias even when the sensitive features are not present. For example, race, gender, etc. can be inferred from other features. Additionally, in many situations, even if making these other features independent of the sensitive features is possible, it is not generally recommended. For example, race, sex, etc. is important in medicine. Now we get to a deeper question. When we mentioned that a fair model produces equivalent predictions for different groups, we did not specify what kind of equality we are considering. Fairness metrics answer this question. But before going there, let us go over some terminology. For a given feature set X and outcome variable Y, we consider a predictor such as a classifier Y hat. The feature A specifies whether a given data point belongs to a sensitive group. And unless specified otherwise, we prefer a prediction of 1. Now, how do we specify a sensitive group? Based on the values of sensitive features, each data point can fall into one of the groups defined by a combination of those features. For example, Black women younger than 25 would be one of the groups when the sensitive attributes are race, gender, and age. Here we describe 3 common criteria of measuring fairness. A model is fair when there is demographic parity, or in other words, there are equal acceptance rates in all groups. A model is fair when it has equalized odds, or when there are equal true positive rate and false positive rates for all groups. A model is said to be fair when it has predictive parity, or in other words, there are equal positive outcome rates given predictive scores for all groups. We won't discuss these in detail here, but one thing to keep in mind is that these are often mutually incompatible, and you may not be able to satisfy all of them simultaneously. So, how do we fix this bias? Most of the interventions can be put into 3 categories. Pre-processing, whereby we make changes to the dataset before training. This can involve selecting relevant features, weighting data points, etc. In processing, where we modify the ML algorithm itself. And post-processing, where we modify the outputs to make those predictions more fair. Let us now turn to the issue of privacy when using AI models. Privacy is essentially about control over personal data. It asks questions such as how and who has access to my data and how it is stored and used. In healthcare and elsewhere, data is extremely sensitive and privacy violations can have legal and ethical consequences. And therefore, handling medical data comes with stricter regulations. In many European countries, the use of personally identifiable information, PII, such as health and demographic data, is regulated by a law known as GDPR. Under this law, misuse of PII is considered a high-risk violation for which defaulting organizations can be fined millions of euros. GDPR protects European Union's citizens' data even when it is processed outside Europe. Notably, under GDPR, individuals have a general right not to be subject to automated decisions. In the US, the law known as HIPAA describes how organizations handle protected health information, PHI. PHI can include any identifiable health information, including medical history, test results, and insurance details that can be linked to an individual. Additionally, although not a binding law, the US Office of Science and Technology Policy's blueprint for an AI Bill of Rights states that persons should be able to opt out of automated systems where appropriate and have access to a human alternative. HIPAA does regulate how patient data can be used for training AI models, but only indirectly. For instance, PHI can be used without patient authorization for treatment, payment, and healthcare operations. For research use, however, an IRB approval might be required. An IRB is an independent committee that reviews, monitors, and approves research involving human subjects. In most cases, patient authorization might be required for using their data, but if the IRB is fully satisfied, it can give its approval to use that patient data. HIPAA generally allows unrestricted use of data if it is de-identified. Here, de-identification imposes stricter requirements about the possibility of information getting linked to an individual than merely anonymization. LLMs, or any machine learning model for that matter, exhibit privacy vulnerabilities due to their tendency to memorize and leak sensitive training data. In this context, privacy attacks exploit the model's internal representation to retrieve confidential training data. Let us now discuss an interesting concept that has gained a lot of traction in this year. AI alignment or alignment means ensuring AI behaves according to human values. One way we control the behavior of AI is by reinforcement learning from human feedback, which enhances an LLM's safety and reliability by adhering to explicit constraints, executing correct instructions, reducing hallucinations, and employing appropriate language. But even if we are sure AI is making decisions according to our values, we should be able to maintain enough control as to prevent AI from making severe mistakes. One important question arises here. Whose values should AI follow, and what are those values? Experiments like this try to answer this question. This figure shows a classical ethical dilemma that the researchers asked multiple people. The researchers asked survey takers whether the autonomous vehicle should kill the pedestrians or the passengers, in case there are no other options. This plot shows the results of the survey. One way to read this plot is that more people prefer things on the right than on the left. For example, more people prefer saving young people, pedestrians, in general, more characters, and humans over pets. This example study illustrates that specifying ethics that the machines should follow is not a straightforward task, and there are some inherent trade-offs. Let us now turn to the last topic in this lecture. Here we try to discuss some other potential social impacts of AI. The use of AI technology can have some adverse impacts on human users. For example, experiments show that individual users tend to use less critical thinking when using generative AI tools such as chatbots, particularly when they have more confidence in the tools than in their own ability. Notably, the current evidence of generative AI's impact on workplace productivity is mixed and inconclusive. But one thing is clear: productivity boost depends on the experience level of the programmer and the nature of tasks involved. One survey reported average productivity gains of 15 to 30% in real-world field experiments, with the greatest improvements observed in well-defined, structured tasks. While generative AI can narrow the experience-based performance gap for entry-level workers, recent research surveys, platform payment data, and administrative records indicate a notable decline in demand for entry-level or novice roles in AI complementary occupations. AI systems, especially LLM-based chatbots, can be overly agreeable or sycophantic, due to which even harmful behaviors may be validated. For example, research indicates that even when users described harmful or illegal behavior, the chatbots often affirmed their choices. Chatbots are also known to enable extremely harmful behavior, including ending one's life. Consequently, some of the issues in the context of AI causing harm are still unresolved. If AI causes harm, who should be held responsible? For example, if Waymo kills someone on the road, who should we prosecute? Should we prosecute the person who booked the cab? Maybe Google? Maybe the software engineer who probably developed that buggy software? These questions are still unanswered. In conclusion, AI systems are not neutral. They reflect data and the design choices. Fairness requires explicit definitions and trade offs. Privacy is evolving alongside new AI capabilities. AI alignment raises fundamental ethical questions. And as AI gets more and more integrated into society, we need to keep an eye on its negative impacts. This slide describes some other references that were used in creating this presentation. Thank you.